Blog Talk Radio.
Hello everyone, I want to welcome all of you back to Ohio Exopolitics. I'm your host, Mark Snyder. I want to apologize about some of the problems we've had with sound quality. I've been working with the people at Blog Talk. I don't know that we've been able to resolve anything yet, but we're still working on it. I'm also going to apologize. I'm probably going to mostly just play a clip tonight, and this is another clip on DNA, and it is related in some ways to Contact 215, where Quetzal and Billy have this discussion about genetic engineering and its uses here on the Earth. Anyway, I'll start this clip and I'll sit back and listen with everyone else.
In 1990, a massive enterprise was launched to identify every single gene that goes into creating a human being. It was called the Human Genome Project.
This had to be the most exciting, momentous kind of science that humankind could have contemplated up until this point. Reading our own instruction book, it is momentous in the sense that you only do it once. If you do it right, that is. Once it's done, and it will basically allow you to cross a bridge that you will never go back across in the future from ignorance into knowledge.
A map of the human genome would help pinpoint the genes involved in major illnesses like cancer, Alzheimer's, and heart disease, offering hope for revolutionary new cures for those affected, and even a way to avoid these diseases for those destined to get them.
Having the human genome is going to transform everything we can do. It's a new foundation for all of science. And medical practice will never be the same. Science will never be the same. Many aspects of society will never be the same again.
Just about everybody I asked to help on this, whether they were Democrats or Republicans, said yes. And I'm grateful that it was, I think, one of the signal achievements of my presidency.
This is the story of an epic endeavor spanning 5 continents, consuming billions of dollars, and lasting over a decade. Its mission was nothing less than to decipher the complete instruction manual for making a human being. This is a real-time simulation of what the human genome looks like. A long strand of DNA coiled up like molecular spaghetti in each cell of your body. Scattered along its length are the thousands of genes that carry the basic instructions to make every component of a human being. Genes are common to all people, but slight variations make each person unique. But until the launch of the Human Genome Project, this was an uncharted universe. Back in the 1980s, labs around the world were searching through DNA for the genes that cause major human illnesses. An unexpected breakthrough emerged from a biological backwater in the small British city of Leicester. On September 17, 1984, while comparing some tiny fragments of human DNA, Alec Jeffreys made a discovery that would turn DNA into a household word.
I just had a gut feeling at the time that this had the potential for being big. Just how big, I haven't got the faintest idea. But I could see this was new, that I did know.
Jeffreys was investigating how diseases run in families. There were many parts of the DNA where he could see inherited patterns, but one region appeared to be unique to an individual, except in the case of identical twins.
I stopped and thought, wait a minute, we've actually got some fantastically variable patterns here. Lots of bits of DNA having a peculiar pattern in a gene, where you've got a short block of DNA repeated over and over again.
This peculiar repeated pattern suggested that it would be ultimately possible to identify every human being in the world with a unique readout, like a barcode.
So they went charging back into the lab and started running around. And, it was very exciting. We thought, we're onto something here. So we all got together and we started drawing up a list of things that this could be used for.
They began gathering samples from all over the lab. Smears on equipment, stains on clothes, rogue hairs, dirty cups, and flakes of skin. They were then able to match each shred of evidence to its owner's unique DNA pattern.
So I thought, okay, we've got possibility here of using this for identification. So we immediately thought forensics. Possibility here, maybe we could use this for establishing family relationships. So immediately started thinking of paternity disputes. We tried hair roots and so on. It was all working. Absolutely amazing. And we looked at brothers and sisters, the other types of close relatives, lots and lots of dissimilarities, even between very close relatives. So it was clear just intuitively that these patterns were essentially completely individual specific. And I think it was at that point that we needed a name. There was a very good friend of mine. He said, well, that's interesting, a bit like fingerprints, aren't they? And that's it. Let's call them DNA fingerprints.
The far-reaching implications of DNA fingerprinting were just beginning to dawn on Jeffries.
I went home that evening and sat down with my wife's suit and showed her all this stuff. And she said, oh, that's great, but you've missed out one area. And so I said, okay, what's that? She said, immigration disputes. And so that's disputes where you've got doubts about claim family relationships. And at that point, I think my blood froze, because I suddenly thought, hang on, if we get into this is no longer just science. This is heavy-duty politics.
Within a year, DNA fingerprinting had settled the first of thousands of immigration disputes, proving this family was entitled to access to Britain. The following year, DNA evidence was first used to resolve a paternity suit. It was the first of millions of paternity cases worldwide. And in 1988, this rapist became the first criminal to be convicted on DNA evidence. Countless offenders have since been identified around the world.
Here was DNA actually saving lives, saving future victims. It's pretty awesome stuff.
Jeffries' serendipitous discovery demonstrated the incredible potential of a tiny section of the human genome. What biologists longed for was to chart the complete set of genetic instructions that make a human being. Scientists knew that DNA was made up of just 4 basic chemical units, known by their initials, G, C, A, and T. Hidden within the endless combinations of letters were the genes that might reveal our evolutionary past and our chance of suffering disease in the future. The key to finding genes was to work out the precise order of these 4 letters along the full length of the DNA strand. But they had no way of reading this sequence. This 4-letter conundrum was solved in Cambridge by one of the great legends in biology, a man with 2 Nobel Prizes, Fred Sanger. He began by cracking the DNA code of a simple virus, but even this tried his patience.
It was a challenge. I mean, there was no sense starting out on human DNA. It would be much too complicated. That's the reason for studying a virus, because they were the only small DNAs. I mean, it would have been nice if we could just, read off the human DNA, but you couldn't.
Even the DNA of something as basic as a virus was too difficult to handle in one long piece. So Sanger began by smashing it up into smaller bits using high-energy sound waves. His breakthrough was to use 4 different chemicals to tag the ends of the DNA fragments. One of them reacted only with fragments that ended with a G. Sorting out these pieces by size, Sanger could locate all the G's in the sequence. The other three chemicals marked the positions of the A's, C's, and T's. By putting the results together, the entire sequence of letters could be revealed. In a 4-lane race, the fragments were sorted by size and letter. Each lane represents a different letter. The smaller pieces traveled faster and settled towards the bottom. The larger fragments remain near the top. In a photo finish, their final positions are recorded on film and the precise order of letters read off.
G, C, A, G, E, G, A. Where are we now? Oh, I see.
But for even the nimblest of fingers, this process called DNA sequencing was tedious. It took Sanger 4 years to work out the virus's full 5,000-letter code. Yet within this seemingly random data, Sanger was able to map out all the genes that run the virus by searching for the telltale letters which begin a gene sequence. Consequently, Fred Sanger became the first person to read the instruction manual of a living organism. His breakthrough meant it was possible for scientists to turn the mirror on themselves and begin deciphering our own instruction code. But they faced a monumental task. It was thought that the human genome contained 3 billion letters of undeciphered code. If Sanger were to have sequenced it himself, it would have taken 2.5 million years. All this data is crammed into every cell of your body. Decoding it would mean launching a project as ambitious as putting a man on the moon. The problem proved irresistible to one of the original discoverers of the double helix. Jim Watson could not resist a fresh challenge, and in 1986 invited 400 scientists to a brainstorming session at his Long Island labs.
Some of the key people who were thinking about big DNA sequencing came. Should we do the human genome sequence? We talked about it, and it was very divisive. A lot of people said, no, it's just too big, too boring. They'd rather do science and just sort of be a technician. And they saw the Human Genome Project as one for technicians.
Tension at the meeting ran high. Many believed the project would launch biology into the major league of big money science, to rank alongside atomic physics and the space program. But opponents like David Botstein were afraid it would jeopardize their regular research.
There were very strong advocates and a fair amount of opposition, and I must say I was among the opponents at that time. And the reason for it was that these advocates saw it as the advent of big biology in the sense of big physics.
It'll be useful. We'd all love to know such a sequence. But the question is, what's the price? What's the price? The rate of DNA sequencing today is of the order of 30,000 person years. 30,000 person years, although a very large number, is not impossible. It's an average size of a space shuttle.
Wally Gilbert, a former physicist, argued for the project.
The project was simply an industrial-scale project, perfectly technically feasible. A single person could work out 100,000 bases of DNA in a year. Therefore, 10 people could work out 1 million. And you could simply scale that up. I could imagine that being done over a 30-year period. That would be of the order of $100 million a year. It would cost of the order of $3 billion.
There was good news and bad news about the $3 billion. The good news was that compared to the kind of money the physicists were used to spending, it was really sort of tissue paper, for the bathrooms. The bad news, that $3 billion was $3 billion that no one had planned on spending.
Many advocates of the Human Genome Project saw Jim Watson as the only person who could persuade Congress to hand over that kind of money. Watson's achievements had earned the respect of many politicians. He argued that the key to understanding cancer and many other genetically based diseases lay in genes that would be found by sequencing the human genome. For Congress, always anxious for some positive headlines, it was too good an opportunity to miss.
Congress likes to hear that you can do something and possibly improve human health. I think it's hard to turn down someone who says, we're going to make America healthier.
In 1990, Congress authorized the Human Genome Project. "100 anonymous donors gave samples of blood and semen, and the task of sequencing their DNA began. Having kick-started the project, Watson's outspoken style soon got him into trouble. In 1992, he was succeeded by another champion of genetic disease research, Francis Collins.
As a physician, it seemed to me this human genome is going to be a medical textbook of unprecedented power. This is potentially the most important organized scientific effort that the human species has ever mounted. What could you compare it to? Splitting the atom? Well, yes, that was a big one, to be sure. Going to the moon, a huge undertaking, a huge achievement. But this one, even more than those, seemed like an adventure into ourselves.
The human genome was too big for a single lab to decode, so they had to figure out how to divide it up. Scattered throughout the genome were the repeated sections of code Alec Jeffreys had stumbled across and used as fingerprints. They stood out like page marks amongst the reams of random code which made up the human genes. If enough could be located, they could be used to draw up a precise map of the genome. Once mapped out, it could be split between 16 labs around the world. Across 5 continents, stretching from Cambridge to Beijing, biologists could then begin sequencing their sections. The completion date was set for 2005. A third of the genome would be sequenced in England at the Sanger Center, a new lab named after the man who started it all. The biologist in charge of this industrial operation had spent most of his career studying the life cycle of tiny nematode worms. John Sulston had no illusions about scaling up for the human genome.
It's rather like driving across a very large country. You need some sort of sense of where the edges of the country are, an atlas sort of view of it. And then if we're going to get to a destination, like London, for example, you have to have another special street map, which will really show you how to home in on your destination. And we might sort of imagine that last stage is like getting the sequence of the human genome. It's a divide and rule process, going down from the big to smaller chunks still, and then analyzing in as much detail as we need to get it all right.
Spreading the human genome around the world might seem like a logistical nightmare, but for Sulston, there was an important principle at stake.
People were able to take particular chunks, and it meant that instead of the human genome being, as it were, owned by a particular country or a particular organization, it was actually shared by everybody. Everybody put in work.
But not everyone was into sharing. Craig Venter, working under Francis Collins, ran one of the public human genome labs in Washington. He thought the public approach needed a shot of adrenaline. After 8 years, only a third of the genome had been sequenced.
Scientists claimed that they were going to do this public program, almost started to believe it was their birthright to get all this money and take the next several decades to do this project. But I kept getting more and more frustrated with the slow, painful pace of it. It was not on a pace where it was going to get sequenced in the next 10 or 15 years.
Venter had a different vision of how to sequence the human genome. He was going to blast the whole thing apart in a process called whole genome shotgun. He proposed bypassing the slow process of mapping by feeding many copies of the sequenced DNA pieces into a supercomputer. It would search for overlapping sections and then reassemble a sequence of letters that make up the genome.
It's like solving a jigsaw puzzle. You pick up a piece and you compare it to all the other pieces until you have one that matches. And if it matches perfectly, you put it together. And then you keep doing that in a serial fashion until you've assembled the whole structure. So it was a totally different mathematical and molecular biology philosophy.
Venter imagined a fully automated sequencing factory with robots feeding data directly into giant computers. He'd heard about a company in Silicon Valley that had just invented a machine that used lasers to read DNA code. It scanned 100 times faster than the human eye.
We wanted to create a laboratory that was the leading edge of interesting things. And two, we had this conviction, if you really wanted to change the world of biology, you would invent new instruments and new kinds of technology. DNA is a digital code. The alphabet of DNA is just 4 different letters. And we were interested in color coding each of the 4 letters and being able to essentially read their order out in these long strings. And the idea that you could actually read out the digital information that was the very core source code for human development was an enormously exciting idea.
I don't think either one of us could probably claim that.
Sorry, folks, you are listening to Ohio Exopolitics tonight. I'm kind of playing it a little low-key, taking it a little easy. We're playing this long clip on DNA. It is related to Contact 215, Henoch Prophecies, because Billy and Quetzal do start to talk about the importance of genetic engineering and that it will eventually be very valuable to the people of the earth. Let's pick back up in our clip that's talking about the sequencing of the human genome.
These were monstrous projects that required thousands of technicians, decades to do, many countries in the case of larger genomes.
But Venter's ideas were rejected by Collins. The snub made Venter feel that perhaps the only way of realizing his vision was to go it alone.
I remember Craig saying he really wasn't satisfied with the rate at which we were progressing. Now, I knew that we were actually progressing at a perfectly good rate, but Craig didn't believe it. He, for whatever reason, and I couldn't talk him out of it. I didn't understand why he was saying, "Oh, it's going too slowly, it's not going to work." And then he disappeared for a while, and I didn't hear any more about him until the spring of '98.
On the 10th of May, 1998, Venter announced that he was launching a rival privately funded bid to complete the human genome years ahead of the public project. The news sent shockwaves around the public project's outposts. Everybody gathered at Jim Watson's Long Island labs for an emergency meeting. Here, Venter revealed to them the reasons for his defection.
Collins' initial response was one of shock. He viewed it just probably as a threat to his existence, his budget.
He had a rather tempestuous discussion, decorated by Jim Watson's comments, who was quite clear what he felt about all of this in terms of it being an effort to do a takeover.
He said the public project was a failure and he had to come in and do it. By that stage, we knew he had an immense ego. I don't think there was any of us who liked him.
It was met with the most intense hostility that I can ever imagine. Watson was using World War II analogies, apparently calling me Hitler.
It's unacceptable. The fact that all this genetic information be controlled by a company, it said in 1984, it was awful. I just thought he was selfish, frankly.
Venter wanted to be the person to sequence the human genome. If he could achieve this in 3 years and beat the public project, there could be a Nobel Prize. The company that manufactured the robot sequencers provided 300 machines for Venter to build the world's largest DNA sequencing factory. He christened the company Celera and gathered DNA samples from 5 donors, one of whom was himself.
I mean, I did it out of scientific curiosity. I in fact, wanted to see my own genetic code. So I did it out of curiosity. I did it out of setting an example. I did it out of, self-examination. Scientific history is full of people using their own material as the subject for investigation. We ended up choosing Celera to demonstrate what we were doing. Celerity is swiftness of action. It's the root for accelerate, and the motto ended up being speed matters. Discovery can't wait.
Celera's plan was to sell the raw sequence data to drug companies and universities, rendering the publicly funded project pointless. The businessman in charge of turning human DNA into a commodity was Tony White. He saw in Craig Venter's idea an opportunity to make a fortune.
Craig, he's an innovator, and he has a great track record in terms of doing, what I call audacious science, and but with calculated risk, not with recklessness. And the idea here was build an information system that people could access for a fee.
There was a feeling of outrage among the public project scientists who believed that human genome information should be freely available to everybody.
You can make an argument, perhaps, I think it's dangerous, for public goods to be produced in this fashion with strings on them. What it means is that the public good is produced and everybody has to pay. And of course we do that. We buy resources, we buy services from companies. That's all right so long as you're on a fairly level playing field. But the thing which I'm intensely aware of with the human genome is this is something that belongs to everybody. And for the rich end of the world, it can make its own rules if it likes. But if it's something which is a universal, global public good, then you can't handle it this way. And I felt, for all of these reasons, that it was extremely important to press ahead with public sequencing to basically undercut this attempt to privatize the human genome, which is what it frankly was.
What really frightened the U.S. part of the public project was that Congress might terminate their funding if a private company could do it for free. Jim Watson was so outraged at the prospect of his life's work being hijacked by big business that he returned to Capitol Hill to plead the public case.
I went down to Washington, got more money from Congress. America has to lead. And there's some things where it doesn't pay to be selfish.
Watson persuaded Congress to spend a further $80 million to keep the public project alive. If it could match Celera's output and make the human genome freely available on the Internet, they could torpedo Celera's business plan. But to achieve this, the public project needed sequencing machines, and they were manufactured by the company that owned Celera.
Well, I didn't plan for it when the government said we're going to really go after it, and can we have these machines too? And because initially they doubted that we would sell them the same equipment because they thought we didn't want them to compete with us. And they were a little surprised when I came back and said, yeah, you can have it. And matter of fact, we'll allocate at least half of the production to you so that you don't get behind. And it was a great time for us commercially. We sold a lot of stuff there.
Tony White charged $300,000 per machine, and hundreds of machines were needed by the public project around the world.
I think it was a win-win situation for Tony White, and of course Tony White quite consciously set up an arms race. He said that either the government effort would collapse, in which case they could make profits out of the genome, or he said the government would have to retool, his words, with the new machines, and so they'd sell the machines twice over, once to Solera in-house and once to everybody else out of house.
With the new machines installed, some labs could churn out 4 million letters a day. That would have taken Fred Sanger more than 3,000 years. Craig Venter had ignited a rocket under the public effort. They began identifying important genes involved in deafness, diabetes, color blindness, and cancer, releasing their data freely onto the web every night. One of the largest public sequencing factories was at the Whitehead Institute in Boston. It was run by Eric Lander.
We bought just about as many machines as could possibly be bought within the budget, but it would have been great if there had been about 2 or 3-fold more funds, because we could have just had a spectacularly close to finished genome done in an even shorter period. And with better, more efficient sequencers, we could in fact ramp up as fast as anybody. Everybody in this building was aware of how much had been sequenced, how many lanes had been sequenced, what it meant, from directors of the groups to the glass washers.
But for the machine minders, it was a constant struggle keeping pace with the robots.
Who are the heroes from the public project? Well, I may be a little biased, but I think it's the people who are actually here and doing the babysitting as much as anyone else. You have to feed them every once in a while with new reagents. We have to go ahead and change their diaper whenever they've made a mess, and give them attention whenever they cry out.
Now that scientists all over the world were able to download gene sequences from the public project's website free of charge, Solera's plans to sell this information were beginning to fall apart. A battle erupted between the two sides. It became headline news.
Well, I think all the media attention to the Genome Project was sort of a two-edged sword. It was a good thing because it brought public attention to a project that really hadn't received a lot of recognition and yet which had the potential to change the world. The downside of it was the stories didn't do a very good job of explaining the science. Instead, they sort of took the easy road towards personality depictions, and that got pretty tiresome.
Collins wanted to avoid a public brawl with Solera that might alienate Congress, so John Sulston in England became Craig Venter's outspoken critic. The dispute came to a head in October 1999.
We're over a year ahead of our aggressive schedule. You were reporting 18 months ago that this was impossible. That
He's not ahead at all. The public program is actually ahead. We have already released 2/3 of the human genome, and he's released nothing at all.
We're so far ahead of our schedule, we decided just to wait and have a complete, accurate one published, and we're going to really have an elegant product out very soon.
And the thing is that he is an absolute master of PR. And he was, I'm quite certain of what was going on. He was sort of teasing the press, you know, come on, dangle the bait, you know.
The disturbing part to me is that it came with all the personal attacks and public acrimony, that it was viewed as a down and dirty competition. They really, you know, that's why the media covered it, right? It was a race.
Every day, Solera pumped out new sequence data and rushed to take out as many gene patents as possible. The plan was to mine this information to devise new therapies and eventually relaunch themselves as a drug company. When they announced they were going to try to patent 6,500 genes, human DNA became Wall Street's hottest commodity.
People got so excited about what Solera was doing and so excited about the future of genomics, and briefly the stock went from $8 up to over $500 a share.
Speculation that Solera was about to file for a patent covering the entire human genome prompted President Bill Clinton to intervene.
This agreement says, in the strongest possible terms, our genome, the book in which all human life is written, belongs to every member of the human race.
While Clinton's statement allowed room for companies to patent individual genes to make targeted drugs, the human genome in its entirety was not for sale. Wall Street went into free fall, sparking the second biggest crash in NASDAQ's history. But the brawl between public and private was damaging more than just the stock market.
As a president, as a matter of policy, I was afraid that it would undermine the scientific progress, that it would delay the mapping, it would delay the practical applications being developed. It would take our eyes off the prize.
The White House needed a go-between, someone who was friends with the leaders of both genome projects. Bill Clinton called in Ari Petrinos to broker a ceasefire.
There were stories that were casting some in terms of good guys and others as bad guys. All of a sudden, everybody was a bad guy. Everybody was out to just make a buck or acquire glory, and that was a turning point as far as I was concerned.
I felt, based on what I knew of it, that they were both useful and they ought to work together. That it was silly that if this thing was done properly, there was more than enough credit to go around.
Petrinos' first effort to unite the two parties was met with frustration. Neither side was prepared to be seen in public with the other. It was time for some private pizza diplomacy.
This didn't have to end up as a train wreck. This didn't have to end up as, a one-man standing kind of outcome.
Petrinos persuaded both men to meet at a secret location.
I think they'd gotten out on a limb that they wished to crawl back off of.
In Ari's basement, they talked over pizza and beer.
Francis was probably the most visibly uncomfortable because I suspect that he still thought of himself as somehow betraying his colleagues by breaking bread with the enemy.
I told no one about this, no one on my staff. Of course, we're doing all this work. We're unaware that I was there in some ways negotiating on their behalf without their blessing. And I felt very strange about that.
There's a lot of, as you can imagine, anti-government sentiment that wanted to see some of the people in the public project truly defeated and humiliated. So I got a lot of grief from those people.
They were in some way captives of their own communities. Leaders may think beyond just the rivalry and the competition and seek some middle ground and compromise. But the people in the ranks and the troops actually want victory.
We sat and talked, probably neither of us wanting to reveal more than the other had, and ultimately realizing that we were, in fact, both within a couple of months of being able to say, I think we have a very good draft of the human genome.
The White House set a 6-week deadline. On Monday, June 26, 2000, both sides would announce the first draft of the human genome together.
We announced that they were going to do it.
Well, folks, there you go. Have it, the draft of the human genome. Going to cut it short this evening. Hit the wall, so to speak. A little tired this evening. Anyway, I hope you've enjoyed it. It's a little off the beaten path. We didn't talk very much about the Meyer case, but in Contact 215, Billy and Quetzal do have quite a discussion on genetic engineering and how important the research is and how important it will be for our future here on the Earth. You've been listening to Ohio Exopolitics. I'm your host, Mark Snyder. Have a good evening.